Hello, my name is Kevin Howarth, and today I'll be presenting mine and my collaborator Jason Hickens' work on the relative efficiency of high-order discretizations of chaotic dynamical systems. Chaotic dynamical systems are common in aerospace engineering applications. The figures on the screen show two examples, a combustion chamber and an aircraft wing. Chaotic systems are characterized by an extreme sensitivity to small changes in initial or boundary conditions, or other parameters such as geometry. Oftentimes we are interested in the instantaneous behavior of these systems, but other times we're interested in studying long time averages of system outputs. Say, for instance, the average lift on that aircraft wing over the course of a takeoff or landing sequence. Let's formalize what we mean by averaging something over a long time. This first equation shows a mathematical definition of a quantity of interest, or QOI, for the rest of this presentation. We have an infinite limit on our time variable tau, which sets the averaging period of this integral. Inside the integral, we have some instantaneous function f applied to u, which is the solution of a differential equation. F can be anything, say a spatial average, for instance. Of course, in practice, infinite time averaging isn't possible, so we approximate the QOI with this second equation. We remove the infinite limit on tau and instead claim that choosing a large value of tau gives us a good enough result. It turns out that the error on this approximation can be shown to decay roughly as 1 over square root tau for some classes of dynamical systems, which is quite slow. This means that no matter how finely we choose our discretization or how high order of a solver we use, our QOI estimate won't improve if the time averaging period tau is too short. This highlights the goal of our work, to study the interplay and trade-offs between discretization error and the QOI approximation error, or standard error as we call it. We do this using two case studies, which I'll now go through in more detail. In the first case study, we look specifically at the interplay between temporal discretization and standard error. We consider the Lorenz equations, a system of ODEs whose chaotic properties are well studied. For our QOI, we'll choose the average value of the z variable in the solution. To solve our ODEs, we choose three explicit schemes with varying order of accuracy. When second order, the classic RK4, as well as an eighth order RK method. Then, for solutions obtained with a given solver, the numerical integration to compute the QOI is performed via quadrature rules with order chosen to match the ODE solver. In order to assess the accuracy of any of the solutions we obtain, we need some sort of truth value. Luckily, since the Lorenz system is so well studied, highly precise solutions do exist. In their work, Kellett and Log provide an extremely precise reference solution along with theoretical analysis supporting its accuracy. So this gives us a reliable true solution of the Lorenz system. We can thus perform an extremely precise time average on this solution, giving us a reference value for our true QOI. One note on the integration. The initial conditions chosen by Kellett and Log are relatively far from the nominal range of solution values demonstrated by the Lorenz system. So the first few time steps of this solution don't really represent the average behavior of the system. In order to avoid weighting our time average with these spin-up period values, we start our integration from t equals 20 instead of 0. Now that we have something to use as a true QOI, we set some final parameters for our simulation. First, we choose a range of time step sizes that covers 3 orders of magnitude, with the largest step size near the stability limit of our numerical schemes. Then, we solve the Lorenz system over 1,000 time units with each combination of step size and solver. For these solutions, we use an initial condition which is already in the regime of nominal solution behavior, so we skip the spin-up period. Finally, we divide these solutions into smaller sample solutions of various lengths, 1, 10, and 100. This is illustrated in the figure at the bottom of the screen. We see that a single large solution can be split into a few medium-length solutions or many short solutions. We then compute the QOI on each of these smaller sample solutions and record the percent errors against the true QOI. Once all this has been done, we can analyze our results. Each of these three subfigures shows data for a constant time averaging period. From left to right, tau equal to 1, 10, and 100. Then, within each subfigure, we plot percent error against time step size. Additionally, we differentiate between the ODE solver methods using the colors and widths of each box plot, as indicated in the legend on the right-hand plot. Finally, each of these box and whisker data points show the quartiles of the percent error from each set of samples. Okay, so what do these plots actually tell us? Firstly, just at a glance, we see that the error values in each plot generally decrease as we look from the left plot to the middle to the right. This illustrates the decrease in standard error with respect to an increase in time averaging period. Now, what can we say about the temporal discretization? Starting with the leftmost plot, we see that when the time averaging period is small, it really doesn't matter what time step size or solver method we use, as the standard error always dominates the discretization error. Moving to the middle plot with the medium time averaging period, this begins to change. At the largest two time steps, we see both higher order methods outperforming the second order method, and there's even some competition between the fourth and eighth order methods at the largest time step. This effect is even clearer in the third plot with the longest time averaging period. Standard error dominates the eighth order method at all time step sizes, but the second and fourth order methods take some number of time steps before their discretization error decays to less than the standard error. So what these plots tell us is that we only benefit from increasing method order, or decreasing time step size, if the time averaging period is large enough that the standard error doesn't dominate. We said before that the standard error is quite slow to converge, so it makes sense that it will dominate your discretization error in most cases, especially when higher order methods are used. Moving on to the second case study, we'll now examine a chaotic PDE, paying attention specifically to the spatial discretization error. We use the modified Kuramoto-Sivashinsky equation as proposed by Blonigan and Wong, and for the QOI, we'll choose the space-time average of the squared solution. This time, since we're focusing on the spatial discretization, we represent spatial derivatives in the KS equation with finite difference schemes of second, fourth, and sixth order. The time stepping is done using a second order accurate rule, and the QOI is evaluated with quadrature rules matched to the order of the finite difference schemes, similarly to the first study. Unfortunately, there aren't any high-precision reference solutions for the KS equation, so we must determine a benchmark value ourselves. We do this using an ensemble of high-order solutions. We obtain these solutions using our sixth-order finite difference rule with a large number of grid points, and our midpoint rule with a very small time step. Additionally, we use a very long simulation period of 10,000 time units. These choices give finer discretizations and longer time averages than any which we use in our sample solutions. So we run 10 simulations with these parameters using random initial conditions and a generous spin-up period, and we average the resulting QOIs to get our estimate for a reference QOI. Finally, as before, we establish our discretization parameters. We use a constant time step size for all simulations and a range of number of grid points between 128 and 256. Then we solve the KS equation 10 times over 4,000 time units, again using randomized initial conditions and a long spin-up period. Lastly, as before, splitting these solutions into sets of smaller solutions gives us our samples, which we use to compute the QOI and compare against the benchmark. Moving on to the results, we have a figure which is directly analogous to the previous results figure. The only difference is that each subplot now has spatial grid spacing on the x-axis instead of time step size. Looking at the trend from left to right across the three plots, we see that increasing the time average period generally leads to a decrease in error for the fourth and sixth order methods. However, the second order method seems to perform roughly the same across the board, indicating that the spatial discretization error of this method dominates the standard error over the range of mesh sizes that we studied. Focusing now on the higher order methods, in the left-hand plot, where the time average period is lowest, we see that the error stays roughly constant with respect to mesh size for these methods, indicating that standard error dominates. In the middle plot, we start to see the mesh size have an effect. Finally, in the right-hand plot, spatial discretization error seems to dominate for the fourth order method across most mesh sizes, as illustrated by the continued decrease in error for that method as mesh size decreases. By contrast, the sixth order method appears to stop improving by around the third step size, at which point standard error again dominates. So these results seem to better highlight the advantages of higher order methods, but there's one more factor to keep in mind: computational cost. Here's a different perspective on the same data. On this plot, we display percent error against CPU time. We have three groups of data corresponding to the three time averaging periods. The linked chains of points within each group indicate the median errors for a method choice over the set of 5 mesh sizes. This plot highlights the efficiency of each method, so which method is least expensive to achieve a given percent error. For example, to achieve a 1% error on this problem, the most efficient choice is the fourth order method with tau equal to 400. If that 1% error is your goal, there's no point further increasing your mesh or using a high order method. In closing, there are two main takeaways from our case studies. First, improving method order only improves your accuracy for large time average periods or large discretizations, for which the standard error may not dominate. And secondly, if a sufficiently large time averaging period is not used, higher order methods do not necessarily improve your efficiency, and they may actually hurt it. As a final note, we would like to stress that high-order methods are still very useful tools for simulating chaotic systems. Our results apply specifically to time averages of chaotic systems, which by nature introduce the slowly converging standard error. Thanks very much for your time, and we hope you enjoyed.